Look up at the night sky on a clear evening and you'll see something that should be impossible. Distant galaxies containing hundreds of billions of stars spinning in perfect spirals that stretch across hundreds of thousands of light years. These cosmic pinwheels have been turning for billions of years, their elegant arms sweeping through space like frozen whirlpools in an ocean of darkness. But here's what will blow your mind. According to everything we know about physics, these spiral patterns should have disappeared long ago. Tonight we're diving into one of astronomy's most beautiful mysteries. Why do galaxies spiral? The answer involves invisible matter that outweighs everything we can see, shock waves that trigger the birth of stars, and gravitational forces so complex they make Einstein's equations look simple. By the end of this journey, you'll understand how the universe creates these magnificent cosmic works of art, and why their very existence reveals secrets about the hidden architecture of reality itself. But before we unravel this cosmic puzzle, hit that like button and subscribe, because we're about to explore forces that operate on scales so vast they dwarf human comprehension. We begin. Picture this. You're standing beside a still pond when someone throws a stone into the center. Ripples spread outward in perfect circles, growing larger and fainter until they disappear at the water's edge. Now imagine that same pond, but instead of water, it's filled with hundreds of billions of stars, and instead of ripples fading away, they persist for billions of years, maintaining their shape as they spiral through space. This is the mystery we're confronting. Why don't galactic spiral arms behave like those pond ripples and simply fade away? When astronomers first discovered that distant galaxies had spiral structures, they assumed these patterns were temporary features. After all, galaxies rotate. Stars closer to the center orbit faster than stars farther out, just like planets in our solar system. Mercury completes its orbit around the Sun in 88 days, while Neptune takes 165 years. This difference in orbital speed should wind up any spiral pattern like thread on a spool, destroying the elegant arms we observe. Scientists call this the winding problem, and it seemed to predict that spiral galaxies should look completely different than what we actually see. If spiral arms were simply groups of stars moving together through space, they would wrap around the galactic center so many times that they'd become unrecognizable smears within just a few 100 million years. But galaxies maintain their spiral structure for billions of years, spinning majestically through the cosmic void as if some invisible force is constantly reshaping their arms. The solution to this puzzle requires us to think about spiral arms in a completely different way. What if they're not permanent structures at all, but rather temporary patterns that constantly form, dissolve, and reform as the galaxy rotates? Imagine standing beside a busy highway at night, watching the headlights of cars create streams of light stretching into the distance. The light pattern appears solid and permanent, but it's actually composed of individual cars constantly entering and leaving the stream. Spiral galaxy arms work similarly, but instead of cars, we're watching stars and gas clouds flowing through regions where spiral patterns naturally form. This breakthrough came from understanding something called spiral density waves. These aren't physical objects you could touch or see directly. Instead, they're pressure waves that move through the galactic disk, like sound waves move through air, creating regions where matter becomes compressed and regions where it becomes rarefied. As stars orbit the galaxy, they periodically pass through these high-density regions, spending more time there due to the increased gravitational pull. The result is that more stars are always present in the spiral arms, even though individual stars are constantly entering and leaving these regions. Think of it like a traffic jam on a circular highway. Cars slow down when they hit the congested area, causing more vehicles to accumulate there, creating a persistent region of high density that moves around the highway, even though individual cars eventually pass through and continue on their way. The traffic jam maintains its identity and location while being composed of constantly changing vehicles. Spiral galaxy arms behave exactly the same way. maintaining their structure while being composed of stars that flow through them over millions of years. But here's where the story gets even more fascinating. These spiral density waves don't just organize existing stars into pretty patterns, they actively trigger the formation of new stars by compressing the gas and dust that fills the space between existing stars. When this interstellar material encounters a spiral density wave, it gets squeezed like a sponge, increasing its density until gravity takes over and begins collapsing the gas into new stellar nurseries. This process explains one of the most striking features of spiral galaxies. The spiral arms appear bright blue because they're filled with young, hot, massive stars that burn with intense luminosity but live for only a few million years. These stellar giants are born in the spiral arms, live their brief but brilliant lives there, and die in spectacular supernova explosions before they can drift away from their birthplace. Meanwhile, older, redder stars that formed in previous passages through spiral arms have had time to spread throughout the galactic disk, creating the yellowish background glow we see between the prominent blue spiral arms. The beauty of this system is that it's self-perpetuating. Spiral density waves trigger star formation, which creates bright regions that make the spiral pattern visible, which helps maintain the density wave structure through gravitational feedback effects. It's like a cosmic engine that runs on its own output, creating and maintaining the spiral patterns that have captivated astronomers for generations. But spiral density waves alone can't explain everything we observe about galactic structure. The mathematics of these waves predict that spiral arms should be much more tightly wound than what we actually see in most galaxies. Real spiral arms typically make only 1 or 2 complete turns around the galactic center, while pure density wave theory suggests they should wrap around many more times. Something else must be influencing the shape and persistence of spiral structures. This is where dark matter enters our story. This invisible substance, which makes up roughly 85% of all matter in the universe, doesn't emit, absorb, or reflect light, making it impossible to see directly. We only know it exists because of its gravitational effects on visible matter. Every galaxy is embedded in a massive halo of dark matter that extends far beyond the visible stars, providing the gravitational scaffolding that holds the entire structure together. Dark matter halos aren't perfectly smooth or spherical. They contain substructures, clumps, and irregularities that create gravitational perturbations throughout the galaxy. These dark matter substructures can trigger the formation of spiral density waves and influence their evolution over billions of years. Computer simulations show that galaxies embedded in lumpy dark matter halos naturally develop spiral structures that closely match what we observe in real galaxies. The interaction between visible matter and dark matter creates a complex dance that shapes galactic evolution. Dark matter provides the stable gravitational foundation, while visible matter responds to density waves by forming stars, which then influence the gravitational field through their mass and energy output. Supernova explosions from massive stars inject energy and momentum into the surrounding gas, creating expanding bubbles that can trigger new spiral waves or modify existing ones. This interplay between dark and visible matter also explains why different types of galaxies have different spiral patterns. Galaxies with more dark matter tend to have more stable, long-lived spiral structures, while galaxies with less dark matter may have more chaotic or temporary spiral features. The ratio of dark matter to visible matter, combined with the galaxy's rotation rate and overall mass, determines the specific type of spiral pattern that develops. Some galaxies display grand design spirals with 2 prominent arms that can be traced almost completely around the galactic disk. Others show multiple arm segments that appear and disappear, creating what astronomers call flocculent or fragmented spiral patterns. Still, others have bars of stars and gas extending across their centers, which create different gravitational conditions that modify how spiral density waves propagate through the disk. Barred spiral galaxies, which include our own Milky Way, represent about 2/3 of all spiral galaxies in the universe. The central bar acts like a gravitational resonance chamber, funneling gas inward toward the galactic center, while launching spiral density waves outward into the disk. This creates a feedback loop where the bar strengthens the spiral arms, and the spiral arms help maintain the bar structure through gravitational torques. The formation of galactic bars themselves represents another layer of complexity in understanding spiral structure. Bars typically form when the central region of a galaxy becomes gravitationally unstable, often triggered by interactions with other galaxies or internal processes like gas inflows or stellar feedback. Once formed, bars can persist for billions of years, continuously influencing the spiral pattern and star formation throughout the galactic disk. Recent observations have revealed that spiral galaxy evolution is far more dynamic than previously thought. Galaxies don't simply form their spiral structure once and maintain it unchanged for billions of years. Instead, spiral patterns can strengthen, weaken, change their pitch angle, or even disappear and reform multiple times throughout a galaxy's lifetime. This dynamic behavior reflects the complex interplay between dark matter, gas dynamics, star formation, and gravitational interactions that constantly reshape galactic structure. The most dramatic changes occur when galaxies interact with their neighbors. Even a close approach by another galaxy can trigger powerful spiral density waves that sweep through the galactic disk, compressing gas and triggering massive bursts of star formation. Direct collisions between galaxies can completely destroy existing spiral structure, mixing the stellar populations and creating entirely new types of galaxies through the merger process. But even isolated galaxies experience ongoing evolution in their spiral structure. Internal processes like gas accretion from the surrounding medium, feedback from active galactic nuclei, and the gradual consumption of interstellar gas through star formation all influence how spiral patterns develop and evolve over cosmic time. Understanding spiral galaxy formation and evolution requires sophisticated computer simulations that model the behavior of dark matter, gas, and stars over billions of years. These simulations have revealed that spiral structure emerges naturally from the fundamental physics of gravity, gas dynamics, and stellar feedback, without requiring any special initial conditions or fine-tuning. The universe appears to be naturally predisposed to create these beautiful spiral patterns whenever the right combination of ingredients comes together. Modern simulations can reproduce the full diversity of spiral galaxy types observed in the real universe, from grand design spirals to irregular flocculent patterns. They show how spiral arms form, persist, and evolve, how bars develop and influence spiral structure, and how interactions between galaxies trigger dramatic changes in spiral patterns. These computational experiments have become essential tools for understanding the physical processes that create and maintain the spiral galaxies we see throughout the cosmos. The story of spiral galaxies is ultimately a story about how the universe organizes matter on its largest scales. From the invisible scaffolding of dark matter to the brilliant light of newborn stars, every component plays a crucial role in creating and maintaining these cosmic masterpieces. The elegant spiral arms we see represent the visible manifestation of invisible forces, pressure waves, and gravitational resonances that operate according to the fundamental laws of physics. As we continue to study spiral galaxies with increasingly powerful telescopes and sophisticated computer models, we're discovering that these structures are even more complex and dynamic than we ever imagined. Each new observation reveals additional layers of physics at work, from the quantum mechanical processes that govern star formation to the relativistic effects near supermassive black holes that influence the behavior of galactic bars. The mystery of spiral galaxies connects to some of the deepest questions in astrophysics and cosmology. How does the universe create such organized, beautiful structures from the seemingly random distribution of dark matter that emerged from the Big Bang? What role do spiral galaxies play in the larger cosmic web of filaments and voids that defines the universe's largest scale structure? How will spiral galaxies evolve as the universe continues to expand and dark energy drives galaxies farther apart? These questions remind us that spiral galaxies are not just pretty pictures in astronomy textbooks. They're dynamic, evolving systems that provide crucial insights into how the universe works on its grandest scales. Every spiral arm tells a story about the interplay between visible and invisible matter, the physics of star formation, and the gravitational forces that shape cosmic structure across billions of years. The physics behind spiral galaxy formation becomes even more mind-bending when we consider the role of magnetic fields threading through galactic disks. These invisible field lines, stronger than Earth's magnetic field, but still incredibly weak by terrestrial standards, stretch across tens of thousands of light-years and play a crucial part in organizing the flow of gas and dust that feeds spiral arm formation. Imagine trying to stir honey with a fork. The thick liquid resists your efforts, creating swirls and patterns that persist long after you've stopped stirring. Galactic magnetic fields work similarly, but instead of honey, they're stirring ionized gas that fills the space between stars. As this magnetized plasma flows through the galaxy, it gets twisted and compressed by rotation and spiral density waves, creating magnetic field lines that align with and reinforce the spiral arm structure. These magnetic fields don't just passively follow the gas motion, they actively influence how gas moves through the galaxy, channeling material along field lines like invisible highways that guide the flow of star-forming material. When gas tries to move perpendicular to these magnetic highways, it encounters resistance that can slow its motion and cause it to accumulate in specific regions, further enhancing the density contrasts that make spiral arms visible. The relationship between magnetic fields and spiral structure creates what astronomers call a dynamo effect. As the galaxy rotates, it stretches and twists the magnetic field lines, amplifying their strength through a process similar to how a bicycle dynamo generates electricity. This amplified magnetic field then influences gas flow patterns, which in turn affects the magnetic field configuration, creating a feedback loop that can sustain spiral structure over billions of years. But magnetic fields introduce their own complications to our understanding of spiral galaxies. Unlike gravity, which always attracts, magnetic forces can both attract and repel depending on the field configuration. This means that magnetic fields can sometimes oppose spiral density waves, creating regions where gas resists compression and star formation becomes suppressed. The delicate balance between gravitational, magnetic, and pressure forces determines where spiral arms form and how long they persist. Recent observations using radio telescopes that can map galactic magnetic fields have revealed structures that look remarkably similar to spiral arm patterns, but slightly offset from the visible spiral arms traced by young stars. This suggests that magnetic fields and spiral density waves are intimately connected, but don't always align perfectly, creating a complex three-dimensional structure that we're only beginning to understand. The temperature of interstellar gas adds another layer of complexity to spiral galaxy physics. Gas in different regions of the galaxy exists at vastly different temperatures, from frigid molecular clouds at -440 degrees Fahrenheit to scorching hot regions around young stars that reach tens of thousands of degrees. These temperature differences create pressure gradients that drive gas flows independent of gravitational and magnetic forces. Cold gas behaves very differently from hot gas when it encounters a spiral density wave. Cold, dense molecular clouds can be easily compressed and triggered to form stars, while hot, tenuous gas tends to resist compression and may even expand when it hits a density wave. This creates a complex, multi-phase medium where different temperature components respond differently to the same spiral wave, leading to intricate patterns of star formation and gas flow that vary throughout the galactic disk. The heating and cooling of interstellar gas creates its own spiral patterns that can either reinforce or compete with gravitational spiral density waves. Massive stars heat their surroundings through intense ultraviolet radiation, creating expanding bubbles of hot gas that push against the cooler ambient medium. When these hot bubbles encounter spiral density waves, they can create shock fronts that trigger new episodes of star formation or disrupt existing star-forming regions. Supernova explosions add even more complexity by injecting enormous amounts of energy into the interstellar medium. A single supernova releases as much energy as our Sun will produce over its entire 10 billion year lifetime, but concentrated into a few seconds. This energy creates blast waves that sweep through the galaxy at thousands of miles per second, compressing gas in some regions while evacuating it from others. These supernova-driven shockwaves can trigger spiral density waves or modify existing ones, creating a connection between individual stellar deaths and galaxy-wide spiral patterns. Computer simulations show that the collective effect of many supernovae can drive large-scale gas flows that help maintain spiral structure, essentially using stellar explosions as engines that power galactic spiral patterns. The timing of supernova explosions becomes crucial for understanding spiral arm evolution. Massive stars that produce supernovae live for only a few million years, so they explode relatively close to where they were born in spiral arms. This means that supernova feedback is concentrated in spiral arm regions, creating intense pressure that can either enhance spiral arm formation through compression or disrupt it through explosive energy injection. The chemical composition of interstellar gas also influences spiral galaxy evolution in ways that astronomers are still discovering. Heavy elements produced by previous generations of stars change how gas responds to compression, cooling, and heating. Gas rich in heavy elements can cool more efficiently, making it easier to compress and form new stars. Gas poor in heavy elements stays hotter and resists compression, making star formation more difficult. This chemical evolution creates gradients throughout galactic disks, with the central regions typically enriched in heavy elements from billions of years of star formation, while the outer regions remain more pristine. These composition gradients influence where and how efficiently spiral density waves can trigger star formation, creating subtle variations in spiral arm properties that depend on galactic chemical history. The role of supermassive black holes in spiral galaxy evolution represents one of the most active areas of current research. Every spiral galaxy contains a central black hole millions or billions of times more massive than our Sun. These gravitational monsters can influence galactic structure through several mechanisms, from the direct gravitational effects of their immense mass to the powerful jets and winds they produce when actively feeding on surrounding material. When supermassive black holes consume matter, they can launch jets of particles at nearly the speed of light, creating powerful outflows that sweep through the galactic disk and influence gas dynamics on scales much larger than the black hole itself. These active galactic nucleus-driven winds can either enhance or suppress star formation depending on their strength and direction, potentially influencing spiral arm formation across the entire galaxy. The gravitational influence of central supermassive black holes extends throughout the galactic bulge and into the inner regions of the disk, where their mass can affect the orbital dynamics that determine spiral wave propagation. Changes in central black hole mass through accretion or mergers can alter the gravitational potential in ways that modify existing spiral patterns or trigger the formation of new ones. Perhaps most intriguingly, recent observations suggest that supermassive black hole activity may be correlated with spiral arm strength in some galaxies. Galaxies with more active central black holes tend to have more prominent spiral structure, though the causal relationship between these phenomena remains unclear. It's possible that spiral density waves help funnel gas towards central black holes, feeding their activity, while black hole feedback influences spiral arm formation throughout the disk. The three-dimensional structure of spiral galaxies adds yet another dimension to our understanding of these cosmic pinwheels. While spiral arms appear as elegant curves when viewed face-on, they're actually complex three-dimensional structures that extend vertically above and below the galactic plane. Stars in spiral arms don't all orbit in perfectly flat circular paths. Instead, they follow slightly inclined orbits that cause them to bob up and down as they circle the galactic center. This vertical motion creates spiral patterns that extend into the galactic halo, where older stars and globular clusters orbit in highly elliptical paths that take them far from the main disk. The gravitational influence of these halo populations can affect disk dynamics in subtle ways, potentially influencing how spiral density waves propagate and evolve over cosmic time. Recent observations using space-based telescopes have revealed that many spiral galaxies show signs of warping, where the outer regions of the galactic disk become tilted relative to the inner regions. These warps can be caused by gravitational interactions with satellite galaxies, dark matter substructure, or the accretion of gas from the intergalactic medium. Warped galactic disks create complex gravitational fields that can trigger new spiral patterns or modify existing ones in ways that depend on the specific geometry of the warp. The study of spiral galaxy formation has been revolutionized by our ability to observe galaxies at different cosmic epochs, essentially watching galactic evolution in action by looking at galaxies at different distances and therefore different ages. These observations reveal that spiral galaxies looked very different in the early universe compared to nearby galaxies we see today. Young galaxies observed when the universe was only a few billion years old tend to have more chaotic, irregular spiral patterns with higher rates of star formation and more active central black holes. As galaxies age and the universe expands, spiral patterns become more organized and regular, star formation rates decline, and central black hole activity generally decreases. This evolution reflects the gradual consumption of gas reservoirs, the buildup of stellar populations, and the changing conditions in the expanding universe. The cosmic environment also plays a crucial role in spiral galaxy evolution. Galaxies in dense clusters tend to lose their spiral structure more rapidly than isolated galaxies, as gravitational interactions with cluster members and the hot intracluster medium strip away the gas needed to maintain spiral density waves. Conversely, galaxies in less dense environments can maintain their spiral structure for longer periods and may even develop more prominent spiral arms through ongoing gas accretion from their surroundings. Understanding why galaxies spiral ultimately requires us to think about these systems as dynamic, evolving entities embedded in an expanding universe filled with dark matter, dark energy, and complex feedback processes that operate across vast ranges of scale and time. The elegant spiral patterns we observe represent the current state of an ongoing cosmic dance between visible and invisible matter, mediated by the fundamental forces of physics operating under conditions that push our theoretical understanding to its limits. Every spiral galaxy tells a unique story about how matter organizes itself under the influence of gravity, rotation, magnetic fields, and stellar feedback. Some galaxies develop grand design spirals that persist for billions of years, while others show more transient, chaotic patterns that constantly evolve and change. The diversity of spiral galaxy types reflects the incredible richness of physical processes that shape these cosmic islands of stars. As our observational capabilities continue to improve and our theoretical understanding deepens, we're discovering that spiral galaxies are even more complex and fascinating than we ever imagined. Each new observation reveals additional layers of physics at work, from the quantum mechanical processes that govern star formation in molecular clouds to the relativistic effects near supermassive black holes that influence the large-scale structure of galactic disks. The mystery of spiral galaxies connects us to the deepest questions about how the universe creates and maintains organized structure on its largest scales. These cosmic pinwheels represent some of the most beautiful and complex systems in nature, where the interplay between matter, energy, space, and time creates patterns that have captivated human imagination since we first pointed telescopes at the night sky. The story becomes even more extraordinary when we examine what happens at the very edges of galactic disks, where spiral arms fade into the cosmic void. Here, in regions so sparse that a single hydrogen atom might drift alone through space the size of a cathedral, we find some of the most surprising evidence for how spiral patterns maintain their grip on galactic structure. These outer regions, called the galactic halo, extend far beyond where most stars shine. Yet even here, tendrils of neutral hydrogen gas trace out spiral patterns that mirror the bright stellar arms closer to the galactic center. This extended spiral structure suggests that the density waves responsible for galactic spirals propagate much farther than astronomers initially realized, reaching into regions where the gravitational influence of the central galaxy becomes almost negligible. What makes this discovery so remarkable is that these outer spiral patterns exist in an environment where conventional physics suggests they should be impossible to maintain. The gas density is so low that individual atoms might travel for millions of years without encountering another particle. The gravitational forces that hold inner spiral arms together become incredibly weak at these distances. Yet somehow, the spiral pattern persists, maintained by processes we're only beginning to understand. The key lies in understanding how information propagates through galactic disks. Spiral density waves don't just move matter around. They carry information about the galaxy's rotation, mass distribution, and dynamic history. This information travels outward through the disk like ripples on a pond, but instead of fading away, it gets amplified and sustained by the complex interplay between different physical processes operating on vastly different scales. Consider how a spiral density wave propagates through a typical galaxy. The wave begins near the galactic center, where the gravitational field is strongest and matter is most densely packed. As it moves outward, it encounters regions with different properties: gas clouds, dust lanes, star-forming regions, and stellar associations all respond differently to the passing wave, creating a complex pattern of compression and rarefaction that depends on the local conditions. In regions rich with molecular gas, the density wave triggers massive star formation events that illuminate the spiral arms with brilliant blue light. These newborn stars pump enormous amounts of energy into their surroundings through stellar winds and ultraviolet radiation, creating expanding bubbles of hot gas that can influence spiral wave propagation across vast distances. But in regions where gas is sparse, the same density wave creates more subtle effects. Here, the wave's influence shows up as small changes in stellar orbits, slight variations in magnetic field strength, and delicate gravitational perturbations that can accumulate over millions of years to create observable spiral patterns, even in the absence of active star formation. This dual nature of spiral density waves explains one of the most puzzling aspects of galactic structure. Why do some spiral arms appear bright and well-defined, while others seem faint and fragmentary? The answer lies in the local conditions that determine how strongly each region responds to the passing density wave. Regions with abundant cold gas and dust respond dramatically, lighting up with intense star formation that makes spiral arms clearly visible. Regions with little gas respond more quietly, creating spiral patterns that can only be detected through careful analysis of stellar motions and magnetic field configurations. The result is that every galaxy displays a unique combination of prominent and subtle spiral features that reflect its individual history and current state. The temporal evolution of spiral patterns adds another layer of complexity to this picture. Spiral arms don't maintain constant brightness or structure over time. Instead, they pulse and flicker like cosmic lighthouses, brightening and fading as density waves interact with the changing conditions in different parts of the galactic disk. This pulsing behavior occurs because star formation is an inherently unstable process. When a spiral density wave compresses gas beyond a critical threshold, it triggers a cascade of star formation that can consume most of the available gas within just a few million years. The resulting stellar winds and supernova explosions then disperse the remaining gas, temporarily suppressing further star formation until new material can accumulate. The cycle repeats as the next spiral density wave passes through the same region, but the local conditions have changed. The gas may have different chemical composition due to enrichment from previous generations of stars. The magnetic field configuration may be altered by previous episodes of stellar feedback. The gravitational environment may be modified by the accumulated mass of stellar remnants left behind by earlier star formation events. These changing conditions mean that spiral arms can appear in different locations during different epochs of galactic evolution. A region that hosted a prominent spiral arm 100 million years ago might show no obvious spiral structure today, while a previously quiet region might suddenly burst into activity as conditions become favorable for density wave amplification. This dynamic behavior helps explain why spiral galaxies show such diversity in their arm patterns. Grand designed spirals with two prominent arms represent galaxies where conditions favor strong, stable density waves that can maintain their coherence across the entire galactic disk. Flocculent spirals with multiple fragmentary arms represent galaxies where local conditions vary dramatically, creating density waves that strengthen and weaken as they propagate outward from the galactic center. The role of galaxy interactions in triggering and modifying spiral patterns cannot be overstated. Even galaxies that appear isolated in space are constantly influenced by the gravitational fields of their neighbors, and these external perturbations can have profound effects on internal spiral structure. When two galaxies pass close to each other, their gravitational interaction creates tidal forces that can stretch and distort both systems. These tidal perturbations propagate inward through each galactic disk, like seismic waves, triggering new spiral density waves or modifying existing ones in ways that depend on the specifics of the encounter. The most dramatic interactions occur when galaxies actually collide and merge, but even distant encounters can leave lasting imprints on spiral structure. A galaxy that experiences a close approach by a massive neighbor might develop asymmetric spiral arms, with one side of the galaxy showing more prominent structure than the other. The gravitational disturbance can also trigger central bar formation or strengthen existing bars, which then influences spiral arm development throughout the galactic disk. Computer simulations of galaxy interactions reveal that these encounters can breathe new life into aging spiral galaxies. Galaxies that have consumed most of their gas through billions of years of star formation can have their spiral structure revitalized by tidal interactions that compress remaining gas reservoirs and trigger fresh episodes of density wave formation. The timing of these interactions becomes crucial for understanding galactic evolution. Early in cosmic history, when galaxies were smaller and more closely packed together, interactions were much more frequent and violent. These early encounters helped shape the fundamental properties of spiral galaxies, establishing the mass distributions, angular momentum profiles, and dark matter halo structures that continue to influence spiral patterns today. As the universe expanded and galaxies became more isolated, the frequency of major interactions decreased, but their effects became more dramatic when they did occur. A galaxy that has evolved in isolation for billions of years can be completely transformed by a single major merger, converting a spiral galaxy into an elliptical system or triggering the formation of entirely new spiral patterns with characteristics unlike anything seen in the pre-merger components. The chemical evolution of galactic disks provides another crucial piece of the spiral galaxy puzzle. Every generation of stars changes the composition of interstellar gas by producing and dispersing heavy elements through stellar winds and supernova explosions. This chemical enrichment alters how gas responds to spiral density waves, creating gradual changes in spiral structure that accumulate over cosmic time. In the early universe, when galaxies contained mostly hydrogen and helium left over from the Big Bang, spiral density waves behaved differently than they do in modern galaxies enriched with carbon, oxygen, silicon, and iron. Gas with low heavy element content cools less efficiently, making it harder to compress into the dense clouds needed for star formation. This means that spiral arms in early galaxies were probably less prominent and more difficult to maintain than the spectacular spirals we see in nearby mature galaxies. As galaxies aged and accumulated heavy elements, their spiral structure became more pronounced and stable. Heavy elements enable more efficient cooling, which allows gas to reach higher densities and form stars more readily when compressed by spiral density waves. The increased star formation efficiency strengthens the feedback processes that help maintain spiral structure, creating a self-reinforcing cycle that makes spiral patterns more robust over time. But chemical evolution also creates gradients within individual galaxies that influence spiral structure in subtle ways. The central regions of galactic disks, where star formation has been most active over cosmic history, become enriched in heavy elements much faster than the outer regions. This creates a radial gradient in gas properties that affects how spiral density waves propagate from the galactic center outward. Gas in the metal-rich inner regions responds more strongly to spiral density waves, creating the bright, well-defined spiral arms we typically see in the central parts of spiral galaxies. Gas in the metal-poor outer regions responds more weakly, creating the fainter, more fragmentary spiral structure often observed at large galactic radii. These chemical gradients also influence the types of stars that form in different parts of spiral arms. Metal-rich gas tends to form lower-mass stars that live for billions of years, while metal-poor gas is more likely to form massive stars that live fast and die young. The resulting variations in stellar populations create subtle color differences along spiral arms that astronomers can use to trace the chemical history of galactic evolution. The discovery of spiral structure in the cosmic web itself has opened entirely new perspectives on why galaxies spiral. The largest scale structures in the universe consist of filaments of dark matter and gas that connect galaxy clusters across hundreds of millions of light-years. Recent simulations suggest that these cosmic web filaments can rotate, creating spiral patterns on scales that dwarf individual galaxies. Galaxies embedded within rotating cosmic web filaments experience gravitational torques that can influence their internal rotation and spiral structure. A galaxy whose rotation is aligned with the cosmic web filament may develop different spiral characteristics than one whose rotation is misaligned. These effects are subtle, but may help explain some of the diversity we observe in spiral galaxy properties. The alignment between galactic rotation and cosmic web structure also affects how galaxies accrete new material from their surroundings. Gas flowing along cosmic web filaments can feed galactic growth in ways that either enhance or suppress spiral structure, depending on how the inflow direction relates to the galaxy's existing rotation pattern. Galaxies that accrete material in the same direction as their rotation tend to develop stronger, more stable spiral patterns, while galaxies that accrete material in the opposite direction may experience disruption of existing spiral structure. The most complex situations arise when galaxies accrete material from multiple directions simultaneously, creating chaotic inflow patterns that can trigger episodic spiral activity, alternating with periods of structural disruption. Understanding these cosmic web influences requires simulations that model galaxy formation and evolution within the full cosmological context, tracking how dark matter halos assemble hierarchically through cosmic time while maintaining the resolution needed to follow detailed spiral structure formation. These simulations represent some of the most computationally challenging problems in astrophysics, requiring supercomputers that can model the universe from its largest scales down to the physics of individual star-forming regions. The results reveal that spiral galaxy formation is intimately connected to the growth of cosmic structure itself. The same processes that create the cosmic web of filaments and voids also determine the properties of dark matter halos that host spiral galaxies. The timing of halo assembly, the frequency of mergers, and the rate of gas accretion all influence how spiral patterns develop and evolve over cosmic history. Galaxies that form early in massive dark matter halos tend to develop different spiral characteristics than galaxies that form later in smaller halos. Early forming galaxies experience more violent assembly histories with frequent mergers that can disrupt spiral structure, while late forming galaxies may develop in more quiescent environments that allow spiral patterns to establish and persist. The cosmic environment also determines the gas supply available for maintaining spiral structure over long periods. Galaxies in dense environments may have their gas reservoirs stripped away by interactions with neighbors and the hot intergalactic medium, causing spiral patterns to fade as star formation declines. Galaxies in sparse environments may continue accreting fresh gas from their surroundings, sustaining active spiral structure for much longer periods. These environmental effects help explain the observed correlation between galaxy morphology and local density. Spiral galaxies are more common in low-density environments where gas stripping is minimal and tidal interactions are gentle enough to trigger rather than destroy spiral structure. Elliptical galaxies dominate high-density environments where violent interactions and gas stripping have erased spiral patterns through merger-driven transformation. The relationship between environment and spiral structure continues to evolve as the universe expands and dark energy drives the acceleration of cosmic expansion. In the far future, as galaxies become increasingly isolated by the expansion of space, environmental effects on spiral structure will diminish, but galaxies will also exhaust their gas reservoirs through star formation, eventually causing spiral patterns to fade as the fuel for new star formation is consumed. The physics of spiral density waves operating in these future low-gas environments may produce spiral patterns unlike anything we observe today. Without abundant gas to provide the material for star formation, spiral arms may become dominated by the gravitational effects of stellar populations and dark matter, creating spiral patterns that are detectable through stellar kinematics rather than the bright star formation regions that make current spiral arms so visually striking. These future spiral galaxies may develop new types of spiral structure based on stellar population gradients, metallicity variations, or the orbital properties of different stellar components. The spiral patterns may become more subtle but also more stable, persisting for much longer periods than the current generation of gas-rich spirals that depend on ongoing star formation to maintain their visibility. Understanding spiral galaxy evolution across cosmic time requires us to think about these systems as temporary manifestations of more fundamental physical processes that operate throughout the universe. The spiral patterns we observe today represent a specific phase in galactic evolution when conditions are just right for density wave formation, gas compression, and active star formation to work together in creating these magnificent cosmic pinwheels. As we continue pushing the boundaries of observational astronomy and theoretical modeling, we're discovering that the question of why galaxies spiral touches on some of the deepest mysteries in cosmology and fundamental physics. These rotating islands of stars serve as natural laboratories where we can study the interplay between gravity, electromagnetism, and the mysterious dark components that dominate the universe's mass and energy budget. The spiral patterns themselves may hold clues to physics beyond our current understanding. Some theoretical models suggest that spiral galaxy rotation curves, which show how orbital velocities vary with distance from galactic centers, may reveal signatures of modified gravity theories or interactions between dark matter and ordinary matter that we haven't yet discovered. Alternative theories of gravity that attempt to explain cosmic acceleration without invoking dark energy make specific predictions about how spiral structure should evolve over cosmic time. Future observations of spiral galaxies at different redshifts may be able to test these theories by measuring how spiral patterns change as we look deeper into the universe's past. The magnetic fields threading through spiral galaxies may also provide windows into fundamental physics operating on cosmic scales. The dynamo processes that amplify and maintain these fields in rotating, conducting fluids represent some of the most complex non-linear phenomena in nature, with potential applications to understanding everything from planetary magnetospheres to the magnetic fields of neutron stars and black holes. The quantum mechanical foundations of star formation within spiral arms reveal another layer of complexity that pushes our understanding to its absolute limits. When giant molecular clouds encounter spiral density waves, they don't simply compress uniformly like squeezing a balloon. Instead, the compression triggers quantum mechanical processes that operate on scales spanning 20 orders of magnitude, from individual atomic interactions to structures larger than solar systems. Inside these collapsing gas clouds, quantum mechanics determines which atoms can stick together to form the first solid particles that will eventually grow into planets. The same quantum processes that govern chemical bonding in a laboratory operate within spiral arms, but under conditions so extreme that they create entirely new types of molecular chemistry. Temperatures approaching absolute zero combine with pressures millions of times greater than Earth's atmosphere to forge complex organic molecules that serve as the building blocks for future planetary systems. These quantum effects cascade upward through multiple scales of organization. Individual molecules cluster into microscopic dust grains, which grow into pebbles, then asteroids, and eventually planets, all while embedded within gas clouds that are themselves organized by spiral density waves spanning tens of thousands of light years. The spiral structure of galaxies thus directly influences the quantum mechanical processes that determine what types of worlds can form around future generations of stars. Recent discoveries have revealed that spiral arms contain not just ordinary matter, but also concentrations of dark matter that participate in the density wave propagation. Dark matter particles, whatever they may be, respond to gravitational forces just like ordinary matter, which means they can be compressed and rarefied by the same density waves that organize visible spiral structure. This creates a feedback loop between visible and invisible matter that we're only beginning to understand. Dark matter concentrations help drive spiral density waves, which compress ordinary matter to form stars, which then influence the gravitational field through their mass and energy output, which affects the dark matter distribution, which influences future spiral wave propagation. The result is a complex dance between two types of matter that we can observe directly and one that we can only detect through its gravitational effects. Computer simulations that include both dark matter and ordinary matter reveal spiral patterns that are more stable and long-lived than those predicted by models that consider only visible matter. The dark matter component acts like a stabilizing framework that prevents spiral arms from winding up too quickly or dissolving into chaotic structures. This suggests that the beautiful spiral galaxies we observe owe their existence not just to the stars we can see, but to the invisible matter that outweighs everything else by factors of 5 to 1. The discovery of intermediate mass black holes within spiral arms has added yet another variable to our understanding of galactic structure. These objects, containing hundreds to thousands of times the mass of our Sun, appear to form when the most massive stars in spiral arms collapse at the end of their brief lives. Unlike their supermassive cousins at galactic centers, these intermediate black holes remain embedded within the spiral structure, orbiting the galaxy along with ordinary stars. As they orbit, these black holes create gravitational perturbations that can trigger additional spiral wave formation or modify existing waves in ways that depend on their mass and orbital characteristics. A spiral arm containing many intermediate mass black holes behaves differently than one dominated purely by ordinary stars, developing different patterns of gas compression and star formation that leave distinctive signatures in the galaxy's overall appearance. The gravitational influence of these black holes extends far beyond their immediate vicinity through a process called dynamical friction. As a black hole moves through the galactic disk, it gravitationally attracts nearby stars and gas, creating a wake of disturbed material that follows behind like the wake of a ship moving through water. These gravitational wakes can persist for millions of years, creating spiral substructure within the larger spiral arms. Some of the most spectacular spiral galaxies show evidence of what astronomers call grand design spiral structure, where two perfectly symmetric arms can be traced almost completely around the galactic disk. These remarkably regular patterns suggest that some special mechanism is maintaining the spiral coherence against all the various processes that should cause the arms to fragment or disappear. The leading explanation involves resonances between different types of gravitational waves that can propagate through galactic disks. Just as musical instruments can produce pure tones when their vibrations occur at specific frequencies, galactic disks can produce remarkably regular spiral patterns when density waves, magnetic waves, and gravitational perturbations from central bars all synchronize at specific resonant frequencies. These resonances are incredibly delicate and can only persist under very specific conditions. The galaxy must have exactly the right mass distribution, rotation curve, and gas content to maintain the synchronization between different wave modes. Small changes in any of these parameters can destroy the resonance, causing grand design spirals to fragment into the more common multi-arm patterns we see in most spiral galaxies. The rarity of perfect grand design spirals suggests that most galaxies exist in states that are slightly out of resonance, creating spiral patterns that are beautiful but not perfectly regular. The imperfections we observe in real spiral galaxies may actually be more typical than the textbook examples of perfect spirals that often appear in astronomy books and documentaries. The study of spiral galaxy dynamics has revealed connections to some of the most fundamental problems in physics and mathematics. The equations that describe spiral density wave propagation are related to those that govern fluid turbulence, plasma physics, and even the behavior of quantum fields in curved spacetime. Solutions to these equations often involve advanced mathematical techniques borrowed from completely different fields of science. For example, the mathematical tools developed to understand spiral shock waves in galactic disks have found applications in studying sonic booms around supersonic aircraft, shock wave formation in fusion reactors, and even the propagation of sound waves through the Earth's interior during earthquakes. The universe appears to use similar mathematical principles to organize matter across an enormous range of scales and environments. The non-linear nature of spiral density wave propagation means that small changes in initial conditions can lead to dramatically different outcomes over time. This sensitivity to initial conditions, similar to the butterfly effect in weather prediction, makes it extremely difficult to predict exactly how spiral structure will evolve in any particular galaxy over billions of years. Computer simulations of galactic evolution must therefore rely on statistical approaches running thousands of different models with slightly different starting conditions to understand the range of possible evolutionary pathways. The results show that while we cannot predict the detailed future of any individual spiral galaxy, we can understand the general principles that govern how spiral structure emerges, persists, and eventually fades as galaxies age and evolve. The role of cosmic rays in spiral galaxy evolution represents another frontier in our understanding of these complex systems. These high-energy particles, accelerated to nearly the speed of light by supernova shock waves and other violent processes, permeate the entire galactic disk and can influence gas dynamics in ways that affect spiral structure formation. Cosmic rays create pressure that can either help or hinder the compression of gas by spiral density waves, depending on their energy distribution and how they interact with magnetic fields threading through the galactic disk. In regions where cosmic ray pressure is high, gas may resist compression, making it more difficult for spiral density waves to trigger star formation. In regions where cosmic ray pressure is low, gas compresses more easily, enhancing spiral arm formation. The production of cosmic rays is intimately connected to spiral structure because most cosmic rays are produced by supernova explosions, which occur preferentially in spiral arms where massive stars are born and die. This creates another feedback loop where spiral structure influences cosmic ray production, which affects gas dynamics, which influences future spiral structure formation. Recent observations have detected cosmic ray-induced gamma-ray emission that traces spiral arm patterns in nearby galaxies, providing direct evidence that these high-energy particles are indeed concentrated in spiral regions. The gamma-ray spiral patterns are slightly offset from the optical spiral arms, suggesting that cosmic rays propagate outward from their sources in spiral arms before radiating away their energy through interactions with interstellar gas and magnetic fields. The three-dimensional structure of cosmic ray distributions may provide new insights into the vertical structure of spiral galaxies and how spiral patterns extend above and below the main galactic disk. Cosmic rays can travel much farther from the galactic plane than the gas and stars that produce them, potentially creating spiral patterns in the galactic halo that mirror but don't exactly match the spiral structure visible in optical light. Understanding the full three-dimensional nature of spiral structure requires observations across the entire electromagnetic spectrum, from radio waves that trace cosmic rays and magnetic fields through infrared light that penetrates dust to reveal stellar populations, to X-rays that reveal hot gas and the effects of stellar feedback. Each wavelength reveals different aspects of spiral structure, and only by combining information across all wavelengths can we hope to understand the complete physics of spiral galaxy evolution. The most ambitious current projects involve coordinated observations of nearby spiral galaxies using space-based and ground-based telescopes operating at different wavelengths simultaneously. These campaigns are revealing that spiral structure is even more complex and multi-layered than previously imagined, with different physical processes creating spiral patterns that overlap but don't always align perfectly. Future space missions will push these multi-wavelength studies to even greater precision, potentially allowing astronomers to create three-dimensional maps of spiral structure that show how density waves propagate not just across galactic disks, but up and down through the full volume of galactic space. These observations may finally answer fundamental questions about whether spiral density waves are primarily two-dimensional phenomena confined to galactic disks, or truly three-dimensional structures that extend throughout galactic halos. The connection between spiral galaxy evolution and the formation of planetary systems adds another layer of significance to understanding why galaxies spiral. The compression of gas by spiral density waves doesn't just trigger star formation, it also determines the initial conditions under which planetary systems form, potentially influencing the types of planets that can exist and their likelihood of developing conditions suitable for life. Stars that form in the dense, compressed gas of spiral arms may develop planetary systems with different characteristics than stars that form in the more quiescent regions between spiral arms. The higher gas densities and different chemical compositions found in spiral arms could lead to the formation of more massive planets, different types of atmospheres, or orbital configurations that are more or less stable over billions of years. The timing of planetary system formation relative to spiral arm passage may also be crucial. A young planetary system that encounters a spiral density wave during its early evolution might experience gravitational perturbations that alter planetary orbits, potentially ejecting some planets from the system while driving others into highly elliptical or unstable orbits. Conversely, planetary systems that form between spiral arm passages might develop in more stable environments, allowing planets to settle into regular orbits that persist for billions of years without major disruption. The location of our own solar system relative to the Milky Way's spiral structure may have played a crucial role in creating the stable conditions that allowed life to evolve on Earth. Recent studies suggest that our solar system currently lies between two major spiral arms of the Milky Way in a region called the Local Arm or Orion Spur. This location may have protected Earth from the intense radiation and gravitational disturbances associated with spiral arm passage, providing the stable environment necessary for complex life to develop over geological timescales. If this hypothesis is correct, then the spiral structure of galaxies doesn't just determine where stars form, but also influences the likelihood that those stars will develop planetary systems capable of supporting life. Galaxies with different spiral patterns might have different probabilities of hosting habitable worlds, making spiral structure one of the factors that determines the distribution of life throughout the universe. The search for life in other galaxies must therefore consider not just whether those galaxies contain the right types of stars and planets, but also whether their spiral structure creates environments stable enough for complex life to evolve and persist over the billions of years required for intelligence to develop. This adds a galactic scale component to astrobiology that connects the largest structures in the universe to the possibility of life emerging on individual worlds. As we continue to study spiral galaxies with ever more sophisticated instruments and theoretical models, we're discovering that these cosmic pinwheels are not just beautiful astronomical objects, but fundamental components of cosmic evolution that influence everything from the formation of chemical elements to the development of planetary systems to the possible emergence of life itself. The spiral arms that have captivated astronomers for generations are revealing themselves to be the visible manifestations of some of the most complex and beautiful physics operating in the universe. Every spiral galaxy tells a unique story about the interplay between matter, energy, space, and time, written in the language of density waves, magnetic fields, and gravitational resonances that continue to challenge our understanding of how the cosmos works on its grandest scales. The mystery of why galaxies spiral ultimately connects to the deepest questions about the nature of the universe itself. These rotating islands of stars serve as cosmic laboratories where we can study the fundamental forces of nature operating under conditions that cannot be replicated on Earth, providing insights into physics that may revolutionize our understanding of reality itself. Each new discovery about spiral galaxy formation reveals additional layers of complexity and beauty in the cosmic dance between visible and invisible matter that shapes the universe's largest structures. As we prepare to explore these questions with the next generation of space telescopes and supercomputer simulations, we stand on the threshold of discoveries that may finally explain why the universe creates these magnificent spiral patterns that have inspired wonder and scientific curiosity since humans first gazed up at the star-filled night sky. The formation of galactic bars represents one of the most dramatic transformations a spiral galaxy can undergo, fundamentally altering how spiral patterns develop and persist across cosmic time. These elongated structures of stars and gas stretch across galactic centers like cosmic highways, channeling material inward while launching powerful density waves outward that can completely reshape spiral arm morphology. When a galactic bar forms, it doesn't simply appear overnight. The process unfolds over hundreds of millions of years as gravitational instabilities in the central regions of galaxies grow and amplify. Stars that once followed circular orbits around the galactic center begin moving in elongated paths that align with each other, creating a coherent structure that can extend across tens of thousands of light years. The physics behind bar formation involves a delicate balance between the stabilizing effects of random stellar motions and the destabilizing influence of the galaxy's own gravity. In younger galaxies, stars move in more chaotic orbits that resist organization into coherent structures. But as galaxies age and their stellar populations settle into more regular patterns, conditions become favorable for bar formation. Computer simulations reveal that nearly every spiral galaxy will eventually develop a central bar if given enough time. The process appears to be almost inevitable, driven by fundamental gravitational instabilities that operate whenever you have a rotating disk of matter with a central concentration of mass. This explains why roughly 2/3 of all spiral galaxies, including our own Milky Way, currently host prominent bars. Once formed, galactic bars become powerful engines that drive spiral structure throughout the entire galactic disk. The bar's gravitational field creates resonances at specific distances from the galactic center, locations where the orbital periods of stars match the bar's rotation period in mathematically precise ratios. These resonances act like cosmic tuning forks, generating spiral density waves that propagate outward with remarkable regularity. The strongest resonances occur at what astronomers call the corrotation radius, where stars complete exactly one orbit in the same time it takes the bar to rotate once around the galactic center. At this special distance, the gravitational influence of the bar creates persistent spiral patterns that can maintain their coherence across billions of years. But bars don't just create spiral structure. They also destroy it in regions where their gravitational influence becomes too strong. Inside the bar region itself, the intense gravitational forces disrupt any pre-existing spiral patterns, replacing them with the elongated structure of the bar. This creates a transition zone where spiral arms either emerge from the ends of the bar or gradually fade into the central regions. The interaction between bars and spiral arms creates some of the most spectacular galactic morphologies observed in the universe. Grand design spirals with two prominent arms often result from bars that have achieved perfect gravitational resonance with their surrounding disks. The bar acts as a cosmic engine, continuously pumping energy into spiral density waves that maintain their strength and coherence as they sweep around the galaxy. Different types of bars create different spiral patterns. Strong bars with high mass concentrations tend to produce tightly wound spirals with steep pitch angles. Weaker bars create more open spiral patterns that make only one or two turns around the galactic center. The bar's rotation speed also influences spiral structure, with faster rotating bars generating different resonance patterns than slower ones. The temporal evolution of barred spiral galaxies reveals a complex interplay between bar strength and spiral arm prominence. Young bars tend to be weaker and produce more chaotic spiral structure. As bars mature and grow stronger, they organize spiral patterns into more regular configurations, but extremely strong bars can eventually suppress spiral structure entirely, creating lenticular galaxies that show little evidence of ongoing spiral density wave activity. The role of gas dynamics in barred galaxies adds another layer of complexity to spiral structure formation. Unlike stars, which respond primarily to gravitational forces, gas can also experience pressure forces, magnetic forces, and shockwave compression that modify how it flows through galactic disks. When gas encounters the gravitational field of a rotating bar, it doesn't simply follow stellar orbits, but can form shock fronts and streaming motions that create entirely different patterns. These gas dynamics explain why many barred galaxies show spiral structure in their gas distributions that doesn't exactly match the spiral patterns traced by their stellar populations. Gas spirals can be offset from stellar spirals, creating complex multi-component structures where different types of matter trace different spiral patterns within the same galaxy. The shock waves formed when gas flows through barred galactic potentials can trigger intense episodes of star formation that create some of the most dramatic spiral arm contrasts observed in any galaxies. The gas gets compressed to much higher densities than would be possible through gravitational forces alone, leading to star formation rates that can be 10 times higher than in unbarred galaxies. This enhanced star formation doesn't occur uniformly throughout barred galaxies, but concentrates in specific regions where gas dynamics create optimal conditions for gravitational collapse. The result is spiral arms with bright knots of star formation separated by darker regions where star formation is suppressed, creating a beaded appearance that traces the underlying shockwave structure. The chemical evolution of barred galaxies proceeds differently than in unbarred systems because bars are extremely efficient at mixing material between different galactic regions. The gravitational torques exerted by bars drive gas flows that can transport material from the outer regions of galactic disks all the way to the central regions in just a few 100 million years. This radial mixing has profound implications for stellar populations throughout barred galaxies. Stars that form in different regions of the galaxy can end up with similar chemical compositions because the gas from which they formed was thoroughly mixed by bar-driven flows. The result is that barred galaxies tend to have more uniform chemical gradients than unbarred galaxies, with less variation in heavy element abundances between central and outer regions. The efficiency of this mixing process depends on bar strength and morphology. Stronger bars create more powerful gas flows that can mix material across larger distances. Bars with different shapes, from nearly circular structures to highly elongated configurations, create different flow patterns that mix material in different ways. Recent observations have revealed that some barred galaxies show evidence of multiple episodes of bar formation and destruction. These galaxies appear to have experienced cycles where bars form, grow strong enough to fundamentally alter galactic structure, then weaken and dissolve, only to reform later with different characteristics. Each cycle leaves its imprint on the galaxy's stellar populations and chemical gradients, creating complex archaeological records of past bar episodes. The destruction of galactic bars can occur through several mechanisms. Major galaxy mergers can completely disrupt bar structure, redistributing stellar orbits in ways that eliminate the coherent motions necessary to maintain bars. Gas inflows triggered by bar dynamics can actually weaken bars by changing the central mass distribution in ways that reduce gravitational instabilities. Perhaps most intriguingly, bars can destroy themselves through their own success in channeling gas toward galactic centers. As bars funnel material inward, they increase the central mass concentration, which can stabilize the galactic disk against the instabilities that originally created the bar. This creates a negative feedback loop where bars gradually eliminate the conditions that allow them to exist. The supermassive black holes found at the centers of most galaxies play crucial roles in bar evolution through mechanisms that operate on vastly different scales. While black holes themselves are microscopic compared to galactic bars, their gravitational influence can extend throughout the central regions of galaxies, affecting the orbital dynamics that determine bar formation and evolution. When supermassive black holes actively accrete material, they can launch powerful jets and winds that remove gas from the central regions of galaxies. This gas removal can weaken or destroy bars by eliminating the material that helps maintain bar structure through gravitational interactions. Conversely, quiet black holes that aren't actively feeding may allow bars to grow stronger by permitting gas accumulation in central regions. The relationship between black hole mass and bar strength shows intriguing correlations that suggest these phenomena influence each other over cosmic timescales. Galaxies with more massive central black holes tend to have weaker bars, while galaxies with less massive black holes often host stronger bar structures. This correlation might reflect the history of black hole growth through bar-driven gas inflows, or it might indicate that black hole feedback suppresses bar formation. The gravitational influence of central black holes also affects the resonance structure that determines spiral arm morphology in barred galaxies. Black holes contribute to the central mass concentration that helps establish resonance locations, but their point-like mass distribution creates different gravitational potentials than the more extended mass distributions of stellar bulges. These differences in gravitational potential structure can shift resonance locations, change the propagation characteristics of spiral density waves, or create entirely new types of resonances that don't exist in galaxies without central black holes. The result is that the spiral patterns in barred galaxies depend not just on bar properties, but also on the masses and activity levels of their central black holes. The study of bar formation and evolution has been revolutionized by numerical simulations that can follow the detailed gravitational dynamics of billions of particles over cosmic timescales. These simulations reveal that bar formation is a remarkably robust process that occurs under a wide range of initial conditions, but the specific characteristics of resulting bars depend sensitively on factors like dark matter, halo properties, gas content, and stellar population characteristics. Dark matter halos play particularly important roles in bar evolution because they provide the gravitational scaffolding within which galactic disks evolve. Halos with different mass profiles, shapes, or concentrations create different conditions for bar formation and can influence whether bars become strong enough to drive prominent spiral structure. The most surprising discovery from these simulations is that bars can form and persist even in galaxies embedded in spherical dark matter halos, contrary to earlier theoretical predictions that suggested bars required triaxial or prolate halo shapes. The key insight is that bars can actually modify their surrounding dark matter distributions through gravitational interactions, creating the conditions necessary for their own persistence. This self-consistency between bars and their dark matter environments helps explain why barred galaxies are so common throughout the universe. Rather than requiring special initial conditions, bars appear to naturally emerge from the gravitational evolution of generic disk galaxies embedded in dark matter halos, making them an almost inevitable feature of spiral galaxy evolution. The formation of rings around barred galaxies represents another spectacular manifestation of the complex dynamics created by bar gravitational fields. These rings, which can contain both stars and gas, form at resonance locations where the orbital periods of particles match the bar rotation period in specific mathematical ratios. Inner rings typically form just outside the bar region at what's called the inner Lindblad resonance, where particles complete multiple orbits around the galactic center in the time it takes the bar to rotate once. The gravitational torques from the bar cause particles at this resonance to follow elongated orbits that intersect to form ring-like structures. Outer rings form much farther from the galactic center at the outer Lindblad resonance, where particles complete a fraction of an orbit in the bar rotation period. These outer rings can extend across the entire visible extent of galaxies, creating spectacular structures that highlight the far-reaching influence of central bars on galactic morphology. The gas dynamics within these resonance rings create ideal conditions for star formation, making rings some of the most active star-forming regions in barred galaxies. The orbital motions that create rings also concentrate gas into narrow regions where gravitational collapse can proceed efficiently, triggering the formation of massive star clusters that light up ring structures with brilliant blue light. Different types of rings form under different dynamical conditions, creating a rich taxonomy of ring morphologies that reflect the underlying gravitational physics. Nuclear rings form in the very centers of barred galaxies, where gas accumulates after flowing inward through bar-driven torques. These central rings often host the most intense star formation in the entire galaxy, creating spectacular displays of stellar birth in regions just a few hundred light-years across. The study of ringed galaxies has revealed that ring formation and destruction can occur cyclically over cosmic timescales. Rings that form during one epoch of bar evolution can be disrupted by changes in bar strength or orientation, only to reform later with different characteristics. This cyclical behavior creates complex ring systems where multiple generations of rings can coexist within the same galaxy. The interaction between rings and spiral arms creates some of the most complex and beautiful galactic morphologies observed anywhere in the universe. Spiral arms can emerge from ring structures, creating galaxies where rings serve as launching points for spiral density waves. Alternatively, spiral arms can terminate at rings, creating structures where spiral patterns fade into ring-like configurations at specific galactic radii. These ring-spiral interactions depend on the precise resonance structure created by bar gravitational fields, which in turn depends on bar mass, rotation speed, and morphology. Small changes in any of these parameters can dramatically alter the locations where rings form and how they interact with spiral structure, creating the wide diversity of barred galaxy morphologies observed in the universe. The temporal evolution of ring spiral systems reveals that these structures are not static features, but dynamic entities that evolve and change over hundreds of millions of years. Rings can grow stronger or weaker, change their shapes, or migrate to different galactic radii as the underlying bar structure evolves. Spiral arms can strengthen or fade, depending on how efficiently rings can launch density waves into the surrounding galactic disk. Understanding these evolutionary processes requires combining observations of galaxies at different evolutionary stages with sophisticated computer simulations that can model the complex gravitational dynamics involved in ring and spiral formation. The results show that barred galaxies represent some of the most dynamically active systems in the universe, where gravitational forces continuously reshape structure on scales ranging from individual stellar orbits to galaxy-wide patterns of star formation. The discovery that our own Milky Way galaxy hosts a prominent central bar has transformed our understanding of spiral structure in our cosmic neighborhood. The bar, which extends roughly 27,000 light-years from the galactic center, influences star formation and chemical evolution throughout the entire galactic disk, including in the region where our solar system orbits. The Milky Way's bar appears to be relatively young by galactic standards, having formed within the past few billion years through gravitational instabilities that developed as the galaxy matured. This recent formation explains why the bar's influence on spiral structure is still evolving, creating the dynamic environment we observe in our local galactic neighborhood. The bar's gravitational field helps explain several puzzling features of Milky Way structure, including the locations of major spiral arms, the distribution of star-forming regions, and the complex gas flows observed in the galactic center region. Understanding our galaxy as a barred spiral system provides crucial insights into how spiral structure forms and evolves in galaxies throughout the universe. The realization that we live inside a barred spiral galaxy also highlights the challenges involved in studying galactic structure from our embedded perspective within the galactic disk. Unlike external galaxies that we can observe face-on, we must piece together the Milky Way's structure from observations made from within the system, creating a perspective similar to trying to map a city while standing on one street corner. Recent surveys using infrared telescopes that can penetrate the dust that obscures our view of the galactic center have revealed the Milky Way's bar structure in unprecedented detail. These observations show that our galaxy's bar is remarkably similar to bars observed in external galaxies, confirming that the physical processes governing bar formation operate universally throughout the cosmos. The study of barred spiral galaxies continues to reveal new aspects of how gravitational dynamics create and maintain the organized structures we observe throughout the universe. Each new discovery adds another piece to the puzzle of understanding why galaxies develop the specific morphologies they display, from the grand design spirals with their perfect symmetry to the complex barred systems with their intricate networks of rings and spiral arms. As we push toward even more detailed observations with next-generation telescopes and more sophisticated computer models, we're discovering that barred spiral galaxies represent some of the most complex dynamical systems in nature. The interplay between bars, rings, spiral arms, and central black holes creates evolutionary pathways that can transform galactic structure in ways we're only beginning to understand. The physics governing these transformations operates across an enormous range of scales, from the quantum mechanical processes that determine star formation rates in spiral shock fronts to the large-scale gravitational dynamics that shape bar evolution over cosmic time. Understanding how these different scales interact requires interdisciplinary approaches that combine insights from fluid dynamics, plasma physics, stellar astrophysics, and cosmology. The remarkable diversity of barred spiral galaxy morphologies reflects the sensitivity of gravitational dynamics to initial conditions and evolutionary history. Small differences in parameters like dark matter, halo concentration, gas content, or merger history can lead to dramatically different outcomes in terms of bar strength, spiral arm morphology, and overall galactic appearance. This sensitivity to initial conditions makes each galaxy a unique experiment in gravitational physics, where the same fundamental forces operating under slightly different circumstances create the rich variety of structures we observe throughout the cosmic landscape. The study of these variations provides crucial tests of our theoretical understanding and reveals the full range of possibilities for how matter can organize itself under the influence of gravity. The story takes an even more extraordinary turn when we consider what happens to spiral structure during galaxy mergers, those cosmic catastrophes that can completely reshape billions of years of careful gravitational architecture in just a few 100 million years of violent interaction. When two spiral galaxies begin their deadly dance toward merger, their individual spiral patterns don't simply add together like overlapping ripples on a pond. Instead, they create interference patterns that can either amplify spiral structure to spectacular levels or destroy it entirely. The early stages of galaxy interaction often trigger the most dramatic spiral activity either galaxy has ever experienced. As the two systems approach each other, their gravitational fields begin to overlap, creating tidal forces that stretch and distort both galactic disks. These tidal perturbations propagate inward like seismic waves, triggering new spiral density waves or dramatically amplifying existing ones. Computer simulations of galaxy mergers reveal that the first close passage between two spiral galaxies can create what astronomers call tidally induced spiral structure. The gravitational pull from the approaching galaxy creates asymmetric forces that launch powerful density waves throughout both systems. These merger-driven spirals often appear more dramatic and chaotic than the regular spiral patterns found in isolated galaxies. The enhanced spiral structure during merger events doesn't just create prettier patterns. It fundamentally alters how gas flows through both galaxies, channeling enormous quantities of material toward the galactic centers where it can trigger explosive episodes of star formation. Some of the most intense starbursts ever observed occur in galaxies undergoing close interactions, with star formation rates that can exceed normal levels by factors of hundreds. These merger-driven starbursts create feedback effects that further modify spiral structure through mechanisms we're only beginning to understand. The massive stars formed during these episodes live fast and die young, exploding as supernovae that inject enormous amounts of energy into the surrounding medium. The collective effect of thousands of supernovae occurring within a relatively small region can blow enormous bubbles in the interstellar medium, creating cavities that disrupt existing spiral patterns while potentially triggering new ones. The magnetic fields threading through merging galaxies experience their own dramatic evolution during these encounters. Field lines that took billions of years to establish in isolated spiral patterns get stretched, twisted, and reconnected in ways that can either strengthen or destroy the magnetic architecture that helps maintain spiral structure. The result is often a chaotic magnetic environment where field lines point in random directions rather than following the organized patterns typical of stable spiral galaxies. As galaxy mergers progress beyond the initial encounters toward final coalescence, spiral structure faces increasingly hostile conditions. The repeated gravitational perturbations from multiple close passages gradually heat up the stellar populations, increasing their random motions until they can no longer maintain the organized orbital patterns necessary for spiral density wave propagation. The elegant spiral arms that once defined both galaxies begin to fragment and dissolve. The final stages of major galaxy mergers typically destroy all traces of spiral structure, converting both galaxies into a single elliptical system with no organized rotational pattern. The stars that once traced beautiful spiral arms become randomly distributed throughout a roughly spherical or ellipsoidal volume, their individual orbital histories erased by the gravitational chaos of the merger process. But not all galaxy interactions lead to complete destruction of spiral structure. Minor mergers, where a small galaxy encounters a much larger spiral system, can actually enhance and rejuvenate spiral patterns rather than destroying them. The gravitational perturbation from the smaller galaxy acts like a cosmic catalyst, triggering new spiral density waves in the larger system while being completely disrupted itself. These minor merger events may be crucial for maintaining spiral structure over cosmic timescales. As galaxies age and consume their gas reservoirs through star formation, their spiral patterns naturally fade and become less prominent. The periodic gravitational kicks from minor mergers can reinvigorate these aging spiral systems. providing the energy needed to launch new density waves and maintain visible spiral structure for billions of additional years. The timing of these minor merger events appears to be crucial for their effect on spiral structure. Mergers that occur when the host galaxy has abundant gas can trigger dramatic spiral enhancement and star formation. Mergers that occur after the galaxy has exhausted most of its gas supply may create spiral patterns that are visible through stellar dynamics but lack the active star formation that makes spiral arms bright and easily observable. The debris from disrupted satellite galaxies doesn't simply disappear after minor merger events. Instead, it gets incorporated into the host galaxy's halo and disk, creating stellar streams and shells that can persist for billions of years. These merger remnants continue to influence the host galaxy's gravitational field in subtle ways that can affect spiral pattern evolution long after the original interaction occurred. Some of the most spectacular spiral galaxies show evidence of recent minor merger events in the form of distorted outer spiral arms, asymmetric structures, or unusual stellar populations that don't match the typical characteristics of spiral arm stars. These galaxies represent snapshots of spiral structure in the process of responding to gravitational perturbations, showing us how dynamic and responsive these patterns can be to external influences. The role of dark matter during galaxy merger events adds another layer of complexity to understanding how spiral structure responds to these cosmic catastrophes. Dark matter halos merge and interact according to their own dynamics, which don't always match the behavior of the visible matter that traces spiral patterns. The result can be situations where the dark matter halo achieves equilibrium while the visible matter continues to show signs of disturbance, or vice versa. The gravitational potential created by merging dark matter halos can create entirely new resonance structures that didn't exist in either of the original galaxies. These new resonances can launch spiral density waves with characteristics unlike anything seen in isolated spiral galaxies, creating merger-induced spiral patterns that challenge our understanding of normal spiral formation mechanisms. Recent observations of galaxy pairs in the process of merging have revealed that spiral structure evolution during these events is far more complex and varied than early theoretical models predicted. Some merging systems show enhanced spiral structure in both galaxies, others show enhancement in just one system while the other becomes disrupted, and still others show immediate destruction of spiral patterns in both components. The specific outcome appears to depend on a complex combination of factors, including the mass ratio between the merging galaxies, their relative orientations, the amount of gas present in each system, and the detailed structure of their dark matter halos. Small changes in any of these parameters can lead to dramatically different evolutionary pathways, making it extremely difficult to predict how spiral structure will respond to any particular merger event. The discovery of spiral structure in the aftermath of galaxy mergers has revealed that these patterns are more resilient than previously thought. Some galaxies that experienced major merger events billions of years ago have managed to redevelop spiral patterns, suggesting that the fundamental physics of spiral density wave formation can reassert itself even after complete disruption of galactic structure. These post-merger spirals often have different characteristics than spirals in galaxies that never experienced major mergers. They may have different pitch angles, different numbers of arms, or different relationships between spiral structure and star formation activity. The merger history of a galaxy leaves permanent imprints on its subsequent spiral evolution that persist long after the original interaction. The study of merger-induced spiral structure has important implications for understanding galaxy evolution in different cosmic environments. Galaxies in dense clusters experience more frequent interactions than galaxies in sparse environments, which means their spiral structure evolves differently over cosmic time. The environmental dependence of spiral galaxy properties may reflect the cumulative effects of numerous minor interactions rather than just the influence of the current local density. As we look towards the future evolution of our own local group of galaxies, the impending merger between the Milky Way and Andromeda galaxies provides a natural laboratory for studying how spiral structure will respond to a major merger event. Current predictions suggest that this merger, which will occur in approximately 4 billion years, will likely destroy the spiral structure of both galaxies, creating a giant elliptical system. But the details of how this merger will unfold remain highly uncertain, depending on factors like the exact trajectories of the approaching galaxies, the amount of gas present in each system at the time of merger, and the response of their respective dark matter halos. The merger might occur as a single catastrophic event, or it might involve multiple close passages that gradually disrupt spiral structure over an extended period. The possibility that minor merger events could continue to influence spiral structure in the merged system adds another layer of uncertainty to these predictions. The numerous satellite galaxies orbiting both the Milky Way and Andromeda could provide ongoing gravitational perturbations that might help maintain some form of organized structure even in the post-merger system. Understanding merger effects on spiral structure requires increasingly sophisticated computer simulations that can model the complex interplay between dark matter, gas dynamics, star formation, and stellar feedback across the enormous range of scales involved in galaxy interactions. These simulations must resolve individual star-forming regions while following the orbital evolution of entire galactic systems, creating computational challenges that push the limits of current supercomputer capabilities. The results of these simulations are revealing that galaxy mergers create some of the most complex astrophysical phenomena in the universe, where processes operating on scales from individual stars to entire galactic halos interact in ways that can either create or destroy the organized structures we observe throughout the cosmic landscape. Each merger event represents a unique experiment in gravitational physics that tests our understanding of how matter behaves under the most extreme conditions found in the universe. The environmental context of galaxy mergers also plays crucial roles in determining their effects on spiral structure. Mergers occurring in the dense cores of galaxy clusters happen in environments filled with hot intracluster gas that can strip material from the merging galaxies and influence the merger dynamics. Mergers in sparse environments occur without these external influences, allowing the intrinsic gravitational dynamics to proceed without interference. The cosmic evolution of merger rates means that spiral structure faced very different challenges in the early universe compared to the present day. When the universe was younger and denser, galaxy interactions were much more frequent and violent, creating conditions where maintaining stable spiral structure was extremely difficult. The beautiful spiral galaxies we observe today may represent a relatively recent phenomenon in cosmic history, emerging only after the universe expanded enough to reduce interaction rates to manageable levels. This evolutionary perspective on spiral structure helps explain why spiral galaxies appear to be more common in the local universe than at high redshifts. Early observations suggested that spiral galaxies were rare or absent in the distant universe, but more recent studies with advanced telescopes have revealed that spiral-like patterns did exist in early galaxies, though they often had more chaotic and irregular morphologies than modern spiral systems. The transition from irregular, merger-dominated early galaxies to the regular spiral systems we see nearby represents one of the major transformations in cosmic history. Understanding this transition requires following how spiral structure formation mechanisms evolved as the universe expanded. Dark matter halos grew larger and more stable, and galaxy interaction rates decreased to levels that permitted long-term structural stability. The chemical evolution of spiral galaxies during merger events creates additional complexity in understanding how these interactions affect galactic structure. Mergers don't just rearrange existing stellar populations, they also trigger intense episodes of new star formation that can dramatically alter the chemical composition of the resulting system. The stars formed during merger-induced starbursts often have different metallicities and abundance patterns than stars formed during quiescent spiral evolution. These chemical signatures provide fossil evidence of past merger events that can persist long after the gravitational effects have faded. Galaxies that experienced major mergers billions of years ago may show unusual abundance patterns or stellar population characteristics that reveal their violent histories, even if their current morphologies show no obvious signs of past interactions. The role of supermassive black holes during galaxy mergers adds yet another variable to understanding spiral structure evolution. When two galaxies merge, their central black holes eventually sink toward the center of the merged system and form a binary black hole pair. The gravitational dynamics of this binary evolution can influence the surrounding stellar and gas distributions in ways that affect spiral pattern formation. Binary supermassive black holes create time-variable gravitational fields that can drive spiral density waves with characteristics unlike those produced by single central masses. The orbital motion of the binary creates periodic gravitational perturbations that propagate throughout the galactic disk, potentially creating spiral patterns that strengthen and weaken in response to the binary orbital phase. When binary black holes eventually merge and coalesce, they release gravitational waves that carry away orbital energy and momentum. This process can create a gravitational wave recoil that kicks the merged black hole away from the galactic center, fundamentally altering the central mass distribution in ways that affect spiral resonance structures throughout the galaxy. The study of post-merger black hole evolution and its effects on galactic structure represents one of the newest frontiers in spiral galaxy research. Gravitational wave detectors are beginning to observe the merger events that mark the final coalescence of binary supermassive black holes, providing direct evidence for processes that were previously only theoretical predictions. Future observations with more sensitive gravitational wave detectors may be able to observe these black hole mergers from much greater distances, potentially allowing us to study how black hole evolution influenced spiral structure throughout cosmic history. The correlation between gravitational wave events and changes in galactic morphology could provide new insights into the relationship between supermassive black holes and their host galaxies. The emergence of multi-messenger astronomy, which combines gravitational wave observations with traditional electromagnetic observations, offers unprecedented opportunities to study how black hole mergers affect their host galaxies in real time. These observations may finally answer fundamental questions about whether supermassive black holes drive galactic evolution or simply respond to changes in their surrounding environments. The complexity of merger effects on spiral structure reflects the fundamental interconnectedness of all components within galactic systems. Stars, gas, dark matter, magnetic fields, and supermassive black holes all respond to merger perturbations in different ways and on different timescales, creating a cascade of effects that can persist for billions of years after the original interaction. Understanding these long-term consequences requires thinking about spiral galaxies as evolving ecosystems where each component influences all others through a complex web of physical processes. The spiral patterns we observe today represent the current state of this ongoing evolution, shaped by billions of years of interactions, mergers, and internal processes that continue to modify galactic structure on timescales far longer than human civilization has existed. As we continue to study spiral galaxies with ever more sophisticated observational techniques and theoretical models, we're discovering that these systems are even more dynamic and interconnected than we ever imagined. Each new discovery reveals additional layers of complexity in the cosmic dance between matter, energy, and gravity that creates and maintains the spiral patterns that have captivated astronomers since we first pointed telescopes toward the heavens. The story of spiral galaxy evolution during mergers ultimately illustrates the remarkable resilience and adaptability of cosmic structure formation processes. Despite the violence and chaos of galaxy interactions, the universe continues to create organized, beautiful spiral patterns that demonstrate the power of fundamental physical laws to generate order from apparent randomness across the vast scales of space and time. The ultimate revelation about spiral galaxies emerges when we examine what happens at the very boundaries of our observable universe, where we're seeing galaxies as they existed when the cosmos was barely a tenth of its current age. These ancient spiral systems challenge everything we thought we knew about how long it takes for the elegant patterns we see today to develop and stabilize. When astronomers first detected spiral structure in galaxies billions of light years away, they expected to find primitive, chaotic systems still in the early stages of formation. Instead, they discovered fully formed spiral patterns that appeared remarkably similar to nearby galaxies, suggesting that the fundamental mechanisms driving spiral formation operated with surprising efficiency even in the violent, dense environment of the early universe. This discovery forced a complete revision of our timeline for cosmic structure formation. If spiral galaxies could achieve their characteristic patterns within just a few billion years of the Big Bang, then the processes we've been studying must be far more robust and rapid than previously imagined. The density waves, magnetic field amplification, and gravitational resonances that create spiral arms apparently operate at maximum efficiency when galaxies are young and gas-rich. The high redshift spiral galaxies reveal another surprising characteristic. Their spiral arms often appear brighter and more prominent than those in nearby galaxies, suggesting that star formation within ancient spiral patterns proceeded at rates that dwarf anything we observe in the modern universe. These cosmic fireworks displays created spiral arms so luminous they remained visible across billions of light years and billions of years of cosmic expansion. The chemical composition of these ancient spiral systems tells a fascinating story of accelerated evolution. Despite their youth, many high redshift spiral galaxies show evidence of substantial heavy element enrichment concentrated within their spiral arms. This suggests that the star formation triggered by spiral density waves was so intense that it rapidly cycled material through multiple generations of stellar evolution, creating and dispersing heavy elements at unprecedented rates. The magnetic field evolution in these early spiral systems appears to have followed similarly accelerated timelines. Observations of polarized light from distant spiral galaxies reveal organized magnetic field patterns that should have taken much longer to develop according to conventional dynamo theory. The rapid rotation and intense star formation in young galaxies apparently created ideal conditions for magnetic field amplification and organization. Perhaps most intriguingly, some of the most distant spiral galaxies show evidence of central bar structures that formed when the universe was less than 3 billion years old. This timeline creates puzzles for our understanding of bar formation mechanisms, which were thought to require much longer periods of disk settling and stellar population evolution before gravitational instabilities could organize into coherent bar structures. The survival of spiral structure across cosmic time in the face of numerous potential disruptions represents one of the most remarkable aspects of galactic evolution. Every spiral galaxy we observe has somehow maintained its patterns despite experiencing countless minor mergers, gas accretion events, stellar feedback episodes, and environmental perturbations that should have destroyed or fundamentally altered their spiral morphology. This resilience suggests that spiral density waves possess self-healing properties that allow them to recover from disruptions and re-establish their patterns even after significant perturbations. Computer simulations reveal that spiral patterns can be temporarily disrupted by various events, but the underlying gravitational and magnetic conditions that create them often reassert themselves within a few 100 million years. The feedback loops between different components of spiral galaxies create a kind of structural memory that helps maintain spiral patterns across cosmic time. When one component of the spiral system is disturbed, other components can provide the gravitational or magnetic framework needed to guide the system back toward its preferred spiral configuration. This self-organization occurs because spiral patterns represent preferred states for rotating galactic disks under the influence of their own gravity. Just as water naturally flows downhill and crystals naturally form ordered lattices, galactic disks naturally develop spiral structure when conditions permit. The universe appears to have a fundamental preference for creating these organized patterns whenever the right combination of mass, rotation, and stability comes together. The discovery of spiral galaxies in the most distant reaches of observable space has profound implications for our understanding of cosmic evolution. If spiral patterns could form and persist from such early epochs, then the universe achieved a level of structural organization much sooner than previously thought. The cosmic dark age, that period between the formation of the first stars and the emergence of organized galactic structure, may have been much shorter than astronomers originally believed. This rapid development of cosmic structure suggests that the physical processes governing galaxy formation operate with remarkable efficiency under the conditions that existed in the early universe. The higher gas densities, more frequent interactions, and different dark matter distributions that characterized the young cosmos apparently created ideal conditions for rapid spiral formation rather than hindering it as some theories predicted. The environmental factors that influenced early spiral galaxy formation were dramatically different from those operating today. The universe was smaller, denser, and filled with primordial gas that had never been processed through stellar nucleosynthesis. These conditions created opportunities for spiral formation mechanisms that don't exist in the modern universe, potentially explaining why some ancient spiral galaxies achieved characteristics that seem impossible to replicate today. The role of dark matter in early spiral formation becomes even more crucial when we consider that dark matter halos were still in the process of assembling when the first spiral galaxies formed. The spiral patterns we observe in ancient galaxies developed within dark matter environments that were actively evolving and growing, creating dynamic conditions that may have actually enhanced spiral formation through ongoing gravitational perturbations. The chemical evolution of spiral arms in early galaxies proceeded under conditions where heavy elements were being created and dispersed for the first time in cosmic history. The first generations of massive stars in spiral arms produced and scattered elements like carbon, oxygen, and iron that had never existed before, fundamentally changing the properties of interstellar gas and enabling new types of star formation processes. This chemical evolution created positive feedback loops that strengthened spiral patterns over time. As spiral arms produced heavy elements, the enriched gas became more efficient at cooling and forming stars, which enhanced the brightness and visibility of spiral structure, while providing more supernova feedback to drive future spiral density wave formation. The magnetic field evolution in early spiral galaxies occurred in an environment where organized magnetic structure was being created from primordial field configurations that were essentially random. The rapid development of coherent magnetic spiral patterns in young galaxies demonstrates the extraordinary efficiency of dynamo processes operating in rapidly rotating, star-forming environments. The interaction between newly formed spiral patterns and the cosmic web filaments that fed early galaxy growth created complex dynamics that we're only beginning to understand. Gas flowing along cosmic web filaments could either enhance spiral formation by providing fresh fuel for density wave propagation or disrupt spiral patterns by introducing material with angular momentum that didn't match the galaxy's existing rotation pattern. The supermassive black holes that grew within early spiral galaxies faced very different conditions than their counterparts in modern galaxies. Surrounded by abundant gas and experiencing rapid accretion, these early black holes may have influenced spiral structure through feedback mechanisms that were much more powerful than anything operating in contemporary systems. The jets and winds launched by actively accreting supermassive black holes in early spiral galaxies could have reached enormous scales, potentially influencing spiral structure throughout entire galactic disks rather than just affecting central regions as they do in nearby galaxies. These feedback effects may have been crucial for regulating star formation within spiral arms and preventing runaway processes that could have consumed all available gas within just a few million years. The study of spiral galaxy evolution across cosmic time reveals that these systems have been remarkably consistent in their basic structure and formation mechanisms, despite the dramatically changing conditions in the universe over the past 13 billion years. The same physical processes that create spiral patterns today were operating with similar effectiveness when the universe was young, hot, and dense. This consistency suggests that spiral formation represents a fundamental mode of organization for rotating matter under the influence of gravity, one that emerges naturally across a wide range of environmental conditions and cosmic epochs. The mathematical relationships that govern spiral density, wave propagation, appear to be universal principles that operate regardless of the specific details of galactic composition or cosmic environment. The preservation of spiral structure across such vast spans of cosmic time and environmental change demonstrates the remarkable stability of these patterns once they become established. The spiral galaxies we observe today are the survivors of billions of years of cosmic evolution, having successfully navigated countless challenges that could have destroyed their organized structure. Understanding why galaxies spiral ultimately requires us to appreciate that these patterns represent one of the universe's most successful solutions to the challenge of organizing matter on galactic scales. From the quantum mechanical processes that govern star formation in molecular clouds to the cosmic web dynamics that feed galactic growth, every aspect of spiral galaxy evolution reflects the operation of fundamental physical laws working together to create and maintain organized structure. The spiral arms that sweep across galactic disks are visible manifestations of invisible forces that operate according to principles we're still discovering. Each new observation and theoretical breakthrough reveals additional layers of complexity in the cosmic machinery that generates these magnificent patterns, reminding us that the universe's capacity for creating organized beauty operates on scales and timescales that challenge human comprehension. The future evolution of spiral galaxies holds secrets that may fundamentally alter our understanding of cosmic destiny itself. As we peer forward through cosmic time, we discover that the spiral patterns captivating us today represent just one chapter in an epic story that will unfold across trillions of years, revealing possibilities for galactic evolution that stretch the boundaries of imagination. In roughly 5 billion years, our own Milky Way will face its greatest test when it collides with the approaching Andromeda Galaxy. This cosmic encounter will serve as the ultimate laboratory for understanding how spiral structure responds to the most violent gravitational disruptions possible. Current simulations suggest that both galaxies' elegant spiral arms will be completely destroyed during the merger, their stars scattered into a new elliptical configuration that bears no resemblance to the organized patterns we see today. But the story doesn't end with destruction. The merged system, which astronomers have nicknamed Milkomeda, may eventually redevelop spiral structure through processes we're only beginning to understand. As the gravitational chaos of the merger subsides and the combined stellar population settles into new orbital patterns, conditions may become favorable for entirely new types of spiral formation that operate according to principles unknown in isolated galaxies. The gas dynamics during such massive mergers create opportunities for spiral regeneration that don't exist in normal galactic evolution. Shock waves propagating through the merged system can establish new density patterns that serve as seeds for future spiral density waves. The magnetic fields torn apart during the collision may reconnect in configurations that enhance rather than inhibit spiral formation, creating magnetic architectures more complex and powerful than anything achieved by gradual evolution. Even more intriguingly, the dark matter distribution in merged systems develops characteristics that may actually favor spiral formation over the elliptical morphologies that emerge immediately after collision. Computer simulations reveal that dark matter halos in post-merger systems often develop substructures and asymmetries that can drive spiral density wave formation through gravitational perturbations operating over hundreds of millions of years. The chemical evolution following major mergers creates conditions unprecedented in galactic history. The intense star formation triggered during collision produces and disperses heavy elements at rates that dwarf normal stellar nucleosynthesis, creating interstellar environments with chemical compositions that may enable entirely new forms of stellar and planetary formation within regenerated spiral arms. These chemically enriched environments may support star formation processes that operate more efficiently than anything possible in first-generation spiral galaxies, potentially creating spiral arms that burn brighter and persist longer than any we observe today. The abundance of heavy elements may also enable the formation of planetary systems with characteristics impossible in metal-poor environments, creating new possibilities for the emergence and evolution of complex chemistry and potentially life itself. The role of supermassive black holes in post-merger spiral regeneration represents one of the most fascinating frontiers in galactic evolution research. When two galaxies merge, their central black holes eventually spiral toward each other and coalesce in events that release gravitational wave energy equivalent to the conversion of several solar masses into pure energy. This process fundamentally alters the gravitational landscape of the merged system in ways that may either enhance or inhibit future spiral formation. The gravitational waves released during black hole mergers can impart recoil velocities that kick the merged black hole away from the galactic center, creating systems with displaced or even ejected central masses. These configurations develop gravitational resonance structures unlike anything seen in normal galaxies, potentially enabling spiral patterns with characteristics that violate our current understanding of how spiral density waves propagate through galactic disks. Alternatively, the merged black hole may settle into the galactic center with a mass and spin configuration that creates more powerful and organized spiral-driving resonances than existed in either progenitor galaxy. The enhanced gravitational field of the more massive black hole may establish resonance zones that extend farther into the galactic disk, potentially creating spiral patterns with greater reach and longevity than anything achievable through normal evolution. The cosmic environment surrounding galaxies will continue evolving in ways that influence spiral structure formation and persistence. As the universe expands and dark energy drives accelerated expansion, the average density of matter and energy decreases, creating increasingly isolated conditions that may actually favor spiral formation by reducing the frequency of disruptive interactions between neighboring galaxies. In this future cosmic environment, spiral galaxies may achieve levels of structural stability and perfection impossible in the crowded conditions of the early universe. Without frequent gravitational perturbations from neighboring systems, spiral density waves may develop characteristics approaching theoretical ideals, creating galaxies with spiral arms that maintain perfect logarithmic shapes and mathematical precision across billions of years. The decreasing cosmic density also affects the supply of fresh gas available for fueling continued star formation within spiral arms. As the universe ages and existing gas reservoirs become exhausted through stellar nucleosynthesis, spiral galaxies must develop increasingly efficient mechanisms for recycling material between stellar generations to maintain the active star formation that makes spiral arms visible. This challenge may drive the evolution of spiral galaxies toward configurations that maximize the efficiency of gas recycling and stellar feedback processes. Future spiral systems may develop spiral arms that operate more like closed ecological systems, where every atom of gas released by dying stars gets efficiently captured and recycled into new stellar generations with minimal loss to the intergalactic medium. The magnetic field evolution in aging spiral galaxies may follow pathways that create field configurations of unprecedented organization and power. As galaxies consume their primordial gas supplies and settle into more stable configurations, the dynamo processes that amplify and maintain magnetic fields may achieve efficiencies impossible in younger, more chaotic systems. These evolved magnetic architectures may enable spiral density wave propagation mechanisms that operate with far greater precision and longevity than anything we observe today. Magnetic fields that took billions of years to develop optimal configurations may support spiral patterns that persist with little change across cosmic epochs, creating galactic structures that represent the ultimate expression of organized electromagnetic and gravitational forces. The three-dimensional structure of future spiral galaxies may evolve toward configurations that maximize the stability and persistence of spiral patterns. Computer simulations suggest that spiral galaxies naturally develop vertical structures that enhance the propagation of density waves both within the galactic disk and into the surrounding halo regions. These three-dimensional spiral patterns may create feedback loops between disk and halo components that reinforce spiral structure in ways impossible in purely two-dimensional systems. Gas and stars orbiting in the galactic halo may follow spiral patterns that mirror and support the density waves propagating through the main disk, creating integrated systems where spiral structure extends throughout the entire galactic volume. The ultimate fate of spiral structure in an expanding universe dominated by dark energy remains one of the greatest mysteries in cosmology. As cosmic expansion accelerates and galaxies become increasingly isolated, the environmental factors that can disrupt spiral patterns will diminish, but so will the sources of fresh material needed to fuel the star formation that makes spiral arms visible. This creates a cosmic race between the perfection of spiral structure through reduced external perturbations and the fading of spiral visibility through declining star formation rates. The outcome may determine whether the far future universe contains galaxies with invisible but perfectly organized spiral patterns detectable only through stellar kinematics, or whether spiral structure itself represents a temporary phase in cosmic evolution destined to fade as the universe ages. The study of spiral galaxy evolution across cosmic time has revealed that these magnificent structures represent far more than mere astronomical curiosities. They serve as natural laboratories where we can observe the fundamental forces of nature operating under conditions impossible to replicate on Earth, providing insights into physics that may revolutionize our understanding of reality itself. Every spiral arm tells a story written in the language of gravity, magnetism, and quantum mechanics, operating across scales that span from individual atoms to entire galactic systems. The density waves that organize spiral structure connect the quantum mechanical processes governing star formation to the large-scale dynamics of dark matter halos, revealing deep connections between different branches of physics that we're only beginning to understand. The mathematical principles underlying spiral formation appear to be universal constants that operate throughout the cosmos, creating similar patterns in systems ranging from weather patterns on Earth to the largest structures in the observable universe. Understanding why galaxies spiral may ultimately teach us about the fundamental tendency of matter and energy to organize itself into complex, beautiful patterns whenever conditions permit. As we continue pushing the boundaries of observational astronomy and theoretical physics, spiral galaxies remain among our most powerful tools for exploring the deepest mysteries of cosmic evolution. These rotating islands of stars continue to surprise us with new discoveries that challenge our assumptions and expand our understanding of how the universe creates and maintains organized structure on its grandest scales. The spiral patterns that have inspired wonder and scientific curiosity since humans first pointed telescopes at the night sky will continue revealing their secrets as we develop ever more sophisticated methods for studying their physics and evolution. Each new discovery brings us closer to understanding not just why galaxies spiral, but why the universe itself seems predisposed to create organized beauty from apparent chaos across the vast scales of space and time. The question of why galaxies spiral ultimately connects to the deepest mysteries about the nature of existence itself, reminding us that we live in a cosmos where mathematical elegance and physical beauty emerge naturally from the fundamental laws that govern reality. These cosmic pinwheels spinning through the darkness represent visible proof that the universe possesses an inherent tendency toward organization and complexity that operates across scales we can barely comprehend, creating patterns of such magnificent beauty that they inspire both scientific investigation and profound wonder about our place in the cosmic story.